Thank you for inviting me to speak today. Yeah, so I'm gonna be following up on Dave's talk that we had seen in the previous hour, and I'll be going into some more of the tropical geometry and combinatorics that display why we have these new results about uh, the Brill-Noether theory over the Hermit space. Let's see. Oh yeah, and yeah, if you need to, just feel free to let me know. I'm not the best at keeping track of chat, so if you want to just unmute yourself, talk to me, that's fine. So when we talk about some joint work with Dave Jensen, what is my purpose today? Well, I want to try to give us an idea of how tropical geometry has provided some new insights into Brill-Noether theory. And really what I want to focus on itself is some of the underlying combinatorics. Mainly because in most of the talks I've given about these results, I've never really had enough time to go into the combinatorics heavily because it kind of explodes, but it's the thing I like the most because it turns into a lot of little fidgety toys and games, and I like fidgety things. So I want to try to emphasize some of the fun that can be had once you get into the mechanics of this. And there's really two results that I want to work towards, because I want to really build up to the K-core partitions and the combinatorial analysis of those, which we use to discuss the splitting loci. But I want to start off with just looking at irreducible components of Brill-Noether loci as a nice little warm-up, so we're not completely flabbergasted by some of the things I'm going to write in the second half of the talk. Now, the two results I want to work towards are looking at, one, how you can produce components. So here is a very big blob of text. What I'm basically telling you is that if I have a general cover in the Hilbert space, and well, if I want to look at the Brill-Noether loci, WRD of C, comma, D, well, I can tell you what the dimension of this is explicitly, as long as I keep track of a couple of conditions. If this looks like a modified Brill-Noether number, and it's modified by this term alpha and K, and we'll get into where this alpha exactly comes from. And you get a little bit stronger than that. Not only can I guarantee you that any irreducible component has a dimension that I can write down explicitly, it's that if I have one of these numbers that satisfies these conditions, I can produce an irreducible component for that as well. And the second result is going to be extending that to the Hilbert space. So you'll note here I have some results where I'm listing publications as opposed to when they were developed. The second theorem is by Larson and myself and Dave Jensen, and it's talking about looking at the dimension of the splitting loci. So I want to look at irreducible components of Brill-Noether loci, and then move on to discuss the dimensions of splitting loci in that order. Now, how do we get there? Well, I'm at least going to say the word tropicalization in the sense of we're going to we tropicalize a curve, typically. Hopefully, we all have a good idea for what happens here, but if not, the the moral of the story is I have a curve, I smash it around, I smush it up, and I get some metric graph gamma out the end of it. Now, we're not going to be concerned about all metric graphs. In particular, we're going to be concerned with the metric graph called the chain of loops, because it is suggestively a chain of loops. The genus of the chain of loops is going to be the number of loops involved. And the length of each loop in this case is going to be very special. I'm not just going to talk about any chain of loops. If I tell you I have a chain of loops of genus G, it's going to be each loop will have a total length that is a multiple of K. This will serve as the tropical analog of a K-gonal curve. Now, one of the reasons we want to really focus on this is due to a few results by Nathan Fleeker in 2017, or that were published in 2017, that said that you can completely describe the divisor theory on a K-gonal chain of loops combinatorially using certain tableau, rectangular tableau. And that he was able to compute the dimension of the Brill-Noether locus of this chain of loops and show that it's an upper bound for the Brill-Noether locus of the K-gonal curve. And then that was followed up, as Dave mentioned earlier, some joint work with him and Drew Ranganathan that showed some lifting techniques to show that this is actually an equality of dimensions and not just an upper bound. Okay, so what are we going to do? I'm going to first introduce the first thing, which is going to be the slight deviation from Brill-Noether theory before. In the classical case, when I wanted to study, say, the Brill-Noether theory of a general curve of genus G, just in the moduli space of genus G curves, you can, again, do a combinatorial analysis and describe the Brill-Noether locus of a certain chain of loops using standard Young tableau, where the number of columns is R plus 1, and the number of rows is G minus D plus R. Well, we're going to do the same thing for these in the K-gonal case, but now we're going to add a slight change to it. We're going to be what we call K-uniform displacement tableau. Right, this is first proposed by Nathan Fleeger. You're going to have a rectangular partition, label it with integers from 1 to the genus, and it's going to satisfy two conditions. First is that you strictly increase in each row and each column, which is not unusual. The second part is going to be the weird one, which is kind of like a modularity condition, which is if I have the same symbol appear in two different boxes, then I need to guarantee that the difference of the coordinates of the boxes is congruent mod K. So for example, this first tableau is a 3 uniform displacement tableau, and we see that the symbol 4 is replaced. And well, if I was to look at the coordinates, I think it is like -1 is what the difference of the coordinates is mod K, or you can kind of do a knight's move, 1, 2, 3 boxes over. So one of the cookie cutter ways of remembering or checking is if it's K uniform is to say, if I see two symbols replaced, the lattice distance between them is a multiple of this uniform distance. So this is 3 uniform, 1, 2, 3. And these are really what I want to focus on when it comes to talking about the Brill-Noether, the WRD of a K-gonal curve.
What is I here?
I is one of the symbols that appears. So in this case, I is equal to 4. All right, so T of XY is just going to be the symbol that appears in that box. X,
but it
y.
doesn't. But the I doesn't appear in the congruence condition.
Yeah, so it is. Yes, correct.
But so in Fleeger's work there was the case, right? There's some torsion order or something, right?
Mm-hmm.
Okay.
Yeah. So one of the most important parts about this is that this gives you a way of defining a family of divisors on this chain of loops, where if a symbol appears in the tableau, it tells you that a chip has to appear on a certain loop in a fixed position, and that congruence condition, whatever that distant or whatever this y minus x is, mod k, that's a distance that it has to appear from a particular vertex.
I see. Okay, thanks.
So this is a way of signing, like, you could think of this as a way of specifying coordinates on WRD. Right. So it turns out that this is actually specifying, like, each tableau defines a torus. This is defined by Fleeger just for the fact that if a symbol doesn't appear, well, I would be free to specify any point on that loop to place, like, say, what we call chips when we talk about divisors on curves, just specifying a particular point with a multiplicity. And, well, one of the things that we want when it comes to working towards how do I talk about the dimensions of these irreducible components is I want to understand these tori. If I can understand the maximal tori with respect to containment, then I can hopefully understand the irreducible components of a Brill-Noether locus. Right. So one thing we want to know is how can I guarantee containment? And well, it just kind of follows from that each torus is something of a set of coordinates that to guarantee containment of tori, well, I need to make sure all the symbols in my larger torus are symbols that appear in my smaller torus. That means there's more conditions that are imposed, or fewer conditions that are imposed. And I need to make sure that the distances, I changed the conditions around, should be y minus x as opposed to x minus y, but -1s on both sides is still fine. And I can guarantee that if I was to mark a point on a loop, that it's marked at the same distance. Right. And that is necessary to prove the two biggest things. One, we need to classify the maximal tori, find the ones that are biggest as possible with respect to containment. And two, showing that they don't pairwise contain each other, which isn't a priori clear just from looking at them, which will hopefully be a little bit more apparent when I try to demonstrate what some of these maximal tori look like. I'm really just going to focus on the first one because the second one is just kind of a slog of checking conditions, and it's not really all that illuminating to why the combinatorics is helpful for us here. Right, so the maximal tori correspond to something that you call a scroller tableau. So I have 3 different tableaux here with 3 different gonality conditions. There's 3 uniform, 4 uniform, and 5 uniform. And I want to try to emphasize something special about these tableaux. If you were to look at all of the symbols that appear in the tableau, well, every symbol that appears can be found, every distinct symbol that appears can be found in this L-shaded region. And not only is it can be found in the L-shaded region, there's also a particular move. It's always I can move over some number of boxes and some number of boxes over and some number of boxes up to find that same symbol repeated. And that's uniform among every symbol. So for instance, in this middle tableau, I can move over 2 and up 2. And I see that 5 repeated. And the same thing holds for every other repeated symbol. The 6, 7, and 8 are both, I see that same exact symbol repeated as I move over 2 and up 2. And for the third example, it is 1, 2, 3, 4, 5, 3 over and 2 up. Now these end up being the maximal tori. And it takes a little bit of work to see that is true. So what is the what do I want to say here? Maybe I should just go on. That's what I mean is that if you give me any rectangular parquet uniform displacement tableau, that I can replace symbols to get a tableau that is scroller, one of these nice L-shaped Knight's tableau. That there is a honest to goodness like algorithmic process to do this by hand if you really wanted to. And the basic idea comes down to moving around something like local obstructions. If I was to just look at any box in my tableau, well, I can look at all of the symbols in the column above and the row to the left, which I might be mirrored, so I might not be seeing this the right, moving my hands the right way, but hopefully the image is good enough. Then I can find a certain number of symbols that are biggest with respect to this. And this ends up being a well-defined hook. And in particular, I'm worried about the k-1 largest symbols. In some sense, these are going to be obstructions to replacing symbols in a uniform fashion. And I want to try to work around these local obstructions. Well, so something that we did was saying, well, you can take these hooks and they have actually some certain really nice properties that allow you to move between them. You can find a path from, because we're writing in the English convention, from the top left of the tableau down to the very bottom right, that will allow you to replace symbols without worrying about these obstructions, and you can do it in a uniform fashion. And when you do this, like, you actually can physically construct a tableau that satisfies the conditions of containment. All the symbols that appeared before are going to be the only symbols that I use, and I won't violate any of the distance conditions. Those won't change, or those modularity conditions. So if symbol I appeared in a box with congruence class -1, it will still appear in a box with congruence class -1 at the end. And there could be many such boxes like this. Okay. Now, how do we actually go about that? Well, these hook lengths we referred to as statistics. Just here is a statistic unit attached to a tab to each box. In my first tableau, I just have a 5 uniform displacement tableau. In the second, I've labeled each box with a statistic up to k-1. And if there are fewer than k-1 symbols up to above a box or to the left of a box in those columns, then we just leave it unlabeled. Right. So for instance, if I look at my top right, the 4 largest symbols are all to the left of the box, as opposed if I look at the symbol that is right above the bottom right, if I look at the 4 largest symbols in this row and column, well, the 2 largest appear to the left and the other 2 largest appear above. So that has a hook length of 2. And then some associated hooks as well. Here's another hook of length 2 and a hook of length 3. Right. These are local obstructions. There's always a path. And here's an example of such a path that winds its way through through the tableau that we had just seen. Right. The statistics, and this here ends up being an admissible path, but there always could be more admissible paths. You could end up getting multiple ways of traveling through and passing around these obstructions. So it's not necessarily a unique construction, and there could be many along this way. Now, I just want to give an example of this procedure. And I'm going to focus on the gonality 3 case, k is equal to 3, trigonal, mainly because it ends up reducing to such a simple idea, which is I'm just going to look at box. I'm going to look at the column above it and the row to the left of it. I'm going to ask, where is the second largest symbol in my tableau? Because if I'm looking at a hook of length at most 2, well, I'm really only looking at the 2 largest symbols. Your largest symbol is guaranteed to be in the bottom right. And so that means the second largest symbol is either directly above it or directly to the left of it. And what I'm going to do is delete the row or column that contains that second largest symbol. For instance, I'll delete the last column, delete the last column again, then I delete the last 2 rows as I travel, or the last 2 rows as I travel up. And so what am I going to do now is I'm actually going to trace backwards through my tableau. I'm going to recreate these steps in the exact opposite order. We ended with a strip that was length 2, and k minus 2, 3 minus 2 in this case is 1. That's going to tell me how I'm going to replace symbols. That will give me the exact L shape that I will have at the end. So I replace the first row, replace the second row. Since I know I have a type 2, that I'm not replacing any symbols yet because there is nothing that is 2 boxes over and 1 box up, until I get to my third step where I add in that third column, or I re-add the third column, and then I will take every symbol that can be moved 2 over and up 1, and I will replace whatever symbol was there before. So we had a 3 and an 8 and a 9 originally in that third column, but they're replaced with a 3 and a 5. The fact that we're using these paths to white and statistics allow us to replace these symbols and not violate any Tableau conditions about increasing or decreasing. And that's really key to this idea here. And replace the last one and shade it with the nice 2 by 1 L-shaped region in this case. Right. And that is the idea, that you can always do this. You can always make all these replacements. Ends up being a nice little cookie cutter process. And then there's always a nice little couple techniques. All I said was, here are these maximal tori, or these things that are maximal with respect to containment. Well, you need to actually show their maximal with respect to containments. So if I have one of these scroller tableau, I can't replace symbols to get another scroller tableau. And then, since this is all taking place downstairs in the Brill-Noether locus of a chain of loops, you apply some lifting techniques that were developed by, say, Dave Jensen and Drew Regonathan to conclude that these are honest-to-goodness irreducible components of Brill-Noether loci. That and a little Perkovich analysis as well. All right. So that's just a way of cutting our teeth on some of the combinatorics that involve, because we're about to spice that up just a little bit to talk about return to these splitting loci. So maybe I just want to pause for a second. Any questions about what I've just talked about? Because I realize I'm probably speaking a little quickly, as I tend to do. Well, all right, let's go on to talking about the second result, which is describing the dimensions of splitting loci. All right, so just as a refresher, that we're going to be talking about branch covers of degree k. If I have a line bundle, I can look at the push forward, which splits as a direct sum of line bundles, which I can write explicitly. Now, some things to take note, that these twists by these integers mu I are unique up to permutation. And so we can assume that these are ordered in a non-decreasing fashion from left to right. This vector is known as the splitting type of a line bundle. And as said before, this is a much more refined invariant. This is a very important piece of information. It doesn't just determine the rank and degree of that line bundle, but the rank and degree of any line bundles pulled back from P1, or all twists of L by line bundles pulled back from P1. So this is a very important property. It gives us a whole lot more information than we had before. And we want to try and recreate everything that we just did. These should explain the irreducible components, and we want to know why. Why is this more important information, and why should it explain everything? And 2, can I recreate the same type of combinatorial analysis? Can I define a notion of a k-uniform displacement tableau that encapsulates the idea of the splitting type? And can I even do the same type of combinatorial analysis that allows me to produce tableau with a minimal number of symbols, so I can try to discuss the dimension of the splitting loci. And one important piece of information that we're wanting to keep track of is what we call the magnitude of a splitting type. Right, this is supposed to be the H1 of endomorphisms, but you can also write this down explicitly using the entries of the splitting type itself. So just as a combinatorial piece of information. This is going to come up a lot. This is actually a much more important piece of information than just a number. Right. Just refresher on this locally closed subscheme, this splitting type locus that we're looking at. But what's the important part is that you can define these same gadgets combinatorially. So much like you can describe the Brill-Noether theory of a chain of loops, you can actually define splitting loci on chains of loops as well, just by modifying the definitions appropriately. And so the important combinatorial result needed to prove the dimensions of splitting loci when it comes to algebraic curves is that if I have a k-gonal chain of loops, that's of genus G, and as long as the genus is at least the magnitude, then I can talk about the dimension of the splitting locus of the k-gonal chain of loops, and it's actually equal to G minus the magnitude, which is the codimension, going to be the codimension of, its codimension is mu, or this magnitude mu, which is equal to the, the rank of a certain tableau, or a certain, the rank of a certain tableau, I'll say tableau, partition in a lattice that we'll see. And moreover, you can actually count, do a point count in the dimension 0 case as a number of maximal chains in the same lattice. Right, so to do this, we need to look at some new types of partitions. We're not going to be able to just talk about rectangular partitions anymore. This lattice comes from the lattice of k-core partitions. But first, we're going to focus on just a small family of partitions that are known as k-staircases. Right, these are going to be k-cores, but they're going to start off with things that we'll first see when we try to generalize the idea of displacement tableau. So what's happening? Well, if I have a splitting type, I'm going to look at a set of information, which is going to basically be trying to say, here is H0 of a twist and H1 of a twist. Now I'm going to describe these combinatorial just in terms of a splitting type. Maybe I don't want to say H0, maybe I do. But what am I trying to do? We're going to, for each of these values, M, you do this for every value of M, you can construct a partition, which is, well, I want all boxes that are to the right or to the left of XM of that splitting type, and all boxes above YM of that splitting type, these two values. Now, this may seem like you could have an infinite number of these things, of these partitions that will arise this way, but it actually ends up being a finite number just from some of the properties of splitting types. If I add M for long enough, if I keep adding M, then eventually these values will be very negative. And so because I have the English convention, I'm still going up and up and up, and I can't have negative boxes. And then if I keep probably doing these backwards, keep subtracting M, if I do a negative enough number, I keep going left and left and left, and I can't have a negative number of boxes. So what do? Is then you define a final partition, lambda of mu, associated to a splitting type just by gluing all of these partitions together along the common box in the top right. And I'll do an example of this to try to give you an idea of what I'm saying here. And this will be what we call a case staircase. This should be the analog of the K uniform displacement rectangular partitions for Brill-Noether loci. And why should you believe that? Well, each one of these is supposed to be capturing, in some ways, a rank and degree of a twist by a particular value. Right, so let's start off with a very small example with a splitting type with 3 entries, -3, -1, 1. Right. And just as a reminder of what these weird things are, xm and ym, well, if I let m be equal to -1, well, I get x of -1 of mu is 1, and y minus 1 of mu is 4. So I should have 1 column and 4 rows. And I can repeat this for 0 and 1. Any other values will get either 0, well, we'll get either 0 for xm or 0 for ym. For m smaller than -1, we get 0 for xm of, we get, 0, and then ym greater than 1, we get 0, or less than 0, equal to 0, should be equal to 0. Okay. And here's the 3 different partitions that we see. 4 rows, 1 column, excuse me, I said the opposite before. 2 rows, 2 columns, 4 columns, 1 row. And we glue these together at the end to get this lambda of mu. Right. So this is a K staircase. And one of the nice things about K staircases is that if I look at an outside corner of the tableau, which is an outside corner is just any box that I could delete and still have a partition at the end, that these are all a lattice distance that is a multiple of the number of entries. In this case, 1, 2, 3, 1, 2, 3. And it's always actually a lattice distance of 1 multiple. Between any 2 consecutive boxes. This is actually a really nicely behaved partition, even if it looks kind of weird. So why do I care about these? Why do I care about these K uniform displacement partitions? Well, if I look at the splitting locus of this chain of loops, I can define K uniform displacement partitions on them, or K uniform displacement tableau, just by filling the boxes with the same conditions, strictly increasing down any row and column, and repetitions satisfy my modularity condition. And the union over all such tori is going to be the splitting locus on the chain of loops. So I can again combinatorially parameterize the splitting locus in terms of tableau and on partitions, on newer, weirder partitions. Okay. Now, it turns out that if I want to go further, I need to actually extend my definition of, or extend the family of partitions I'm looking at. I want to look at K-cores, this slightly larger family. Right? And one of the nice things about this family of partitions is that it ends up being a ranked lattice. And we're secretly going to take advantage of that a lot. And I'll try to make it explicit of how we take advantage of the fact that it is a ranked lattice. Right? So one thing is that K staircases are K cores. And that if I look at a certain poset associated to a K staircase, that this is actually an interval in this poset of K cores. It's the interval below this, this K staircase. Right. And here's an example of one of these integrals. We take that splitting type partition that we just built, these minus the empty partition are all of the k-cores that appear below it in the partition of, or in the lattice of k-cores. Some of these are also staircases, like these, but not all of these are staircases, or k staircases, 3 staircases. Like this is not a 3 staircase, and these are also, I guess these are like trivially 3 staircases, but not everything you get in that integral is going to be that. So this is like one of the reasons that we started looking at k-cores, is we said, well, is there a nice way of trying to remove certain boxes? Much like in our previous work, we said, let's try to delete rows and columns. That ended up being like way too rough and ready to really make reasonable. So we said, is there a way of removing certain boxes? And that naturally led us to consider partitions that didn't arise naturally from a splitting type outside of deleting things. And there's also going to be something that's important to note here, which is if you look at the magnitude of the splitting type, -3, -1, 1, that the magnitude is equal to 5. And if I try to trace out 1, 2, 3, 4, well, there would be an empty partition here. But if I wanted to trace out the length of any maximal chain, that length is equal to 5 as well. And that idea is something that we want to take advantage of later, these maximal chains. But how do we actually get this interval? Like, why did I delete? If you look at the difference between the top one and the next one, it comes from deleting all outside corners. Whereas if you look at the difference between the next step, I deleted only a particular outside corner. Right? So like, if I want to try to take advantage of these maximal chains, then I need to really understand why I deleted certain corners. Sometimes I delete a lot, sometimes I delete one. And why do I always delete something? Right. So to work towards that, just as a note that, because we're looking at a subinterval of a ranked lattice, full lower order ideal, this is also going to be a length ranked lattice, and the length is equal to the rank of that element in the poset. And it turns out that the rank of this element is equal to the magnitude of the associated splitting type. And if I want to describe the dimension of the splitting type locus, well, I need to recreate exactly what I did before, which is instead taking the union over all tori, I want to try to remove as many redundancies as possible and describe it as the union over all tori with the fewest number of symbols. I want to replace symbols until I can't replace anymore. And that ends up being exactly the magnitude. So already you can tell that things are working a little bit nicer. Before, when I talked about irreducible components, I could replace symbols and get, well, tori with very different dimensions, but now I'm guaranteed to always be able to replace symbols and get the exact same number in after each of these replacements, even though they all could be unique replacements. Right. And we're going to do this constructively again. We're going to sit there and start with a k-uniform displacement tableau on this weird partition, and we're going to replace symbols until we have one with the smallest number of symbols. But we need to kind of rework what we did before. Deleting rows and columns and statistics don't work quite as well in this setting as they did in the previous setting. So how do we decide which boxes we're going to need to delete at every step? And the two key things that come in mind are operations known as upward displacement and downward displacement. Now, what exactly is this? Well, given a congruence class mod k, I can define a certain diagonal to be the set of all boxes on my partition where the congruence class of the difference of their coordinates is equal to a. Maybe I should go back and show here, like in this case, here is, say, the diagonal 0. Here's the diagonal 1, diagonal 2, diagonal 3. These would be diagonals if I just draw a straight line down to the right and all boxes passing through it. So why do I care about these diagonals? Well, I want to start worrying about something that we call removing symbols or adding symbols. Upward displacement. So since we're using English convention and not French convention, this may sound a little backwards, but the upward displacement of lambda with respect to a and z mod k is the partition obtained from lambda by adding all outside corners in the diagonal mod a. And the downward displacement is going to be the same idea, but removing all inside corners in that diagonal. So outside corner is everything I could add and still have a partition, and inside corner is everything I can delete that it would still result in a partition. And why do I really care about these operations of upward and downward displacement? Well, if you look at the family of k-core partitions, this ends up being an invertible operation, like they undo each other. If I take the upward displacement with respect to a, z, and z mod k, and then the downward displacement, I end up with the same partition I started with, and vice versa. Right. This operation gives the ranking on the lattice. And one way that you can view the post set of all k-cores is by starting with the empty partition and then just looking at the post set of, I'm sorry, it should be partitions and not tableau, generated by all possible sequences of upward displacements with cover relations by upward displacing by a single congruence class. Right. This is what gives it the property of being a ranked lattice. And the rank is just the number of upward displacements needed to generate a particular partition. And as mentioned before, the rank of a K staircase is precisely the magnitude. Okay, right. So we're going to produce a procedure that's to prove the theorem about the dimension of the splitting locus of the chain of loops in the same way that we did for proving the dimension of the Brill-Noether locus, or the dimensions of each irreducible component. Right, so what are we going to do? Well, if I have a K staircase with a certain filling, so if I have a K uniform displacement tableau, well, I want to look at all outside corners of this partition. And I want to consider two pieces of information. I want to consider the congruence classes of these corners. So this isn't as important for a staircase, but it is for a K-core. And I also want to consider the symbol that appears in each corner. Out of the set of pairs, I'm going to look at the congruence class of I'm sorry, that shouldn't be outside corners there. That should be inside corners. So apologies about that. It should be symbols in your tableau. They should be boxes in your tableau. So should be look at all of the symbols and the inside corners that you can delete, and I want to find the biggest one. And then I'm going to take every inside corner that appears in a diagonal A mod K and delete those. That is a downward displacement of lambda with respect to A. you could keep track of this. You'll have a skew tableau. I'll have the tableau I started with, and the new tableau from downward displacement. And that's a skew tableau. And in that skew tableau, I can replace all of the symbols with that largest symbol. I'll have a actual example after this to better illustrate what's happening here. And we're going to keep repeating this process. We're going to repeat this process for every tab, like all the smaller tableau. Keep track of the fact that we've done some downward displacements and we have a skew tableau beneath it with replace symbols. And we're going to repeat that until I just delete every box. And I have the new skew tableau is the original tableau I started with symbols replaced. Now, what is actually happening here? We're going to go back to that splitting type -3, -1, 1 that we saw before. This is a K uniform displacement tableau. In this case, a 3 uniform displacement tableau on that K staircase. Well, in this case, there's only one single congruence class of inside corners. It is the inside corner, there's only one single congruence class of inside corners for a K staircase. So the first step is always the easiest. I've deleted all my inside corners. And in the skew tableau, I've replaced all the symbols. 7 and 5 are now the largest symbol in the tableau, and 8. And I'm left with a tableau that the partition 3, 1, 1. And now I have two possible inside corners. I have an inside corner with a 4, an inside corner with a 6. Well, these are in different congruent classes because 1, 2, 3, 4 is not a multiple of 3, fortunately, in this sane world. I'm going to delete the inside corner with the 6 because it's the largest symbol. And since it's the only symbol, the only box I deleted, I didn't need to worry about replacing any other symbols. Again, I have two possible choices at this next step. I could delete either the 3 or the 4. Well, technically 2 choices, but 1, 2, 3 is one choice. So I lied to you. I delete these inside corners and I replace that 3 with a 4. And then I would do this again, but changing now the 1 and the 2 is not, deleting those isn't going to do anything. So we have replaced the symbols and we can count how many distinct symbols there are. 1, 2, 3, 4, 5, which is the magnitude of the splitting type. If you wanted to trace this out, this is actually following one of those maximal chains in the partition of K cores, or in that interval below this partition. And I was hedging my bets on speaking much more slowly than I have. And I'm a little done with this. So there's a whole lot that goes into this. So I'll end with a few things that there's a lot more that we can do with this. You know, like for instance, we explored the combinatorics, the combinatorial side of this a lot on the tropical, on the chain of loops. You can actually show it's the splitting locus is connected in codimension 1 by keeping track of these maximal chains and making small alterations. At the dimension 0 case, this is a point count. And we did lots and lots of examples of trying to enumerate these point counts. You see lots of different numbers come up. You'll see Fibonacci, exponential, binomial, pretty much any type of class of integer, counting integer Catalan numbers, like comes up, and they come up very quickly for all different types of things. So And it all ends up being kind of another interesting piece of information, which is another way that you can look at the magnitude is by a particular set of columns in your tableau and a piece of like how tall those columns are. And there's another, like this ends up being like another sequence, or you can call it another vector that you can play around with by, subtracting or adding numbers appropriately to different entries. And this kind of gives you an idea of another way of playing around with the magnitude and playing around with getting these point counts to come up. But that's detailed a little bit more in our paper. Lots of examples. There's no like nice closed forms expressions for them outside of you have very particular splitting types, like some very special ones that you can sit down and say, well, I know it's always going to be exponential or Fibonacci. But if I just have a three uniform, like a splitting type of like 3 without anything special about it, then it could have like say any number of that could. 3 is not a good example, but like if I have a splitting type of like 4, then the point count might not have a closed form expression just without like really getting your hands dirty with it. So I think I am going to pause there and stop rambling semi-coherently, quasi-coherently, because that is a much more pithy joke.